Thank you, Professor Sheep, for the introduction. So my project is an optical system with applications in metaphysics and astronomy. I'd also like to thank Dr. Gary Jernigan and the other students who have helped me. So the specific system that I was working with is something called a coded aperture. And a coded aperture is essentially a system with a basically a metal mask with a bunch of holes drilled in it and a specific pattern that will be discussed earlier, how that pattern is constructed, and a detector from which photons will pass through and you can detect it, and then a system to reconstruct your image based on that detector. So to start with the coded and then the goals of this project is I wanted to create, use a coded aperture to reconstruct three-dimensional information from a coded aperture system. And this was going to be done using linear systems theory, Monte Carlo techniques, and by numerically creating a neutral mask pattern. So essentially, this guy here, if you have a source, photons will pass through the mask to the detector, and then I want to back project everything to figure out where it is in X, Y, and Z. Okay, so to start off, we should look at a pinhole camera. So a pinhole camera is essentially the simplest coded aperture, and you are able to focus an image. So this is often done in photography. If any photographers in here, they've probably heard of pinhole cameras. So you can basically focus an image and has a large depth of field. One of the problems though is it blocks almost all the light, so you need a long exposure time. So for pinhole photography, a lot of times the exposure takes about half an hour. Then also, if anyone here has ever watched a solar eclipse, it's the same idea where you have a plate with a hole drilled in it because you're not supposed to look directly at the sun. So you want to basically create an image on the ground and watch that guy. So a coded aperture is essentially a pinhole camera, but instead you have basically a bunch of holes, and then you get a bunch of images on there. So it allows more photons to pass through. You can do a bunch of math stuff to kind of reconstruct where everything is, but certain patterns are going to create more noise. And as an object moves closer to the mask, there's going to start being more angular separations in your images over here. And so what I wanted to do was basically harness those angular separations to figure out where something is not just an X, Y, but also Z. And something to note is this is a linear system. Okay, so I'm going to briefly go into the math. I'm more than happy to answer any questions afterward. So something to note, this is a linear system. And something about linear systems is if you know the input and you can figure out what the transfer function is, you can directly figure out what your output is going to be. So if F is your input, H is your transfer function, G would be your output. And so here's basically, it's an integral transform, or you can write it in terms of a discrete transform, where it's your input, transfer, and output. And something to note is that for a pinhole camera, the transfer function is a delta function. And delta function is basically a function that is infinitely tall and infinitely thin, but such that the area under that curve is exactly 1. And something to note is when performing this convolution, which is this process right here, when you convolve anything with a delta function, you get that function back. Something else to consider is when designing the mask, we're going to want the mask to be such that mask can convolve with mask. And where did the pointer go? So with that point source there, we project lines from that source to the detector. All right, so that'd be essentially a convolution, a manual convolution. And then with that, I'm going to back project the photons back, which is what these dashed lines are for. And so we can kind of figure out where something is in X, Y, and Z. And the more holes you get, the better this process is. And after many iterations, we can figure out where it is in 3D. Okay, and so as far as some basic calculations of how this is done, this is basically a lot of doing a lot of similar triangles. So if we have D1, R1, 2 from the source to the mask, and then we can figure out from the mask to the detector, knowing the distance between the two, and then doing some similar triangle math right there. Okay, so when simulating the data, if we have this mask pattern, and we horizontally shift the source moving to the right, I believe, we can see the mask pattern shifting to the left with these guys right here. And so basically it's working when shifting it. Another thing to note is that we should also see how it's moving when it's moving closer and farther away. So given the same mass pattern, as it moves farther away, we would hope that we'd see more of the mass pattern as it moves back, which we do see. So basically that's a confirmation that looks like how I'm simulating the data works. And then from there, I can back project and figure out where something is in 3D. So given 2 point sources, which is kind of hard to see here, if I have a point source right there and a point source there, those little red dots, and this is everything oriented 3D. We go from these point sources going through the mask to the detector, and basically this color bar of how many detections on that detector. I can back project those through back in 3D to get these guys here, and going from black to white is the number of back projected photons in that specific area. And so as we can see here, we're starting to get some location stuff. You see something going on there, something going on there, but it's kind of noisy right now. So from then on, I started working on cleaning up the data, which I did through background subtraction. So I basically, from this set here, I add a random Gaussian value to each position and subtract the two. And any negative values were set to 0. And then also something to note is that things get darker as things move away. As moving away from the detector, there's less back projections. So I'd sum up the total number of back projections in each slice and then try to normalize each one to a specific level. And so that's basically, from this cleaning process, it'll go from before to after, so things definitely start to look a lot better. And this is everything oriented in 3D again. So if we look at this guy with that point source here, just slide closer. There's not much going on to get the next one. You start seeing some stuff going on, slide after it goes away. And for this second point source, we're able to tie it down in X and Y really well, but not so well in Z. You can see it starts coming up in between these three. I wouldn't really be able to tell you where it is in Z, and the slide after it starts going away. So something I did notice when reconstructing is that closer is better. It's kind of because you have a higher angular resolution, so this separation really helps. So something you can do to kind of cement that in your mind is if you hold your finger up close to your face and you blink each eye, you can kind of see that finger move. And then when you move farther away, your finger moves less. So it kind of makes sense that closer is better for that. And when I mean closer is better, close as in within half the total width of your detector. Okay, so in conclusion, we were able to reconstruct 3D information with a stationary detector. So a lot of times something like a CT scan, you have something that spins around your object to get 3D information. Well, this is actually just done without moving at all. We can still make the algorithm better, try to make the images more clear, and also I'm starting to use this with the CZT array, which Kevin had talked about earlier. So this could be used with the CZT system, and so this is an image of a single pinhole using CZT. And so I'd like to thank Dr. Jernigan, Dr. Hong-Tao Shi, Ben Cunningham, Kevin Zach, and Buck McCready, and SSU for giving me an opportunity to work on this project.